Namaste and welcome to this lecture on linear algebra through geometry. I'm quite sure, you've gone through the lectures on the singular value decomposition. You've understood what singular value decomposition does, and we also did eigenvalue decomposition some time back. What we're going to do is we're just going to look at some interpretations of this eigendecomposition and singular value decomposition. And we looked at the eigendecomposition for a real symmetric matrix. We're going to take things from there. So we'll just do recall of eigendecomposition for real symmetric matrices with distinct eigenvalues. That's very interesting thing. That's something we're going to look at. And then we will look at the singular value decomposition where we had U sigma V transpose. We'll see similarity between eigendecomposition and this U sigma V transpose and try to interpret it a bit differently, right? So interesting interpretation we're going to have. Okay, so let's look at this. So recall. If A n by n is a real symmetric matrix with distinct eigenvalues, then the corresponding eigenvectors are orthogonal to each other. The corresponding eigenvectors are orthogonal to each other. And we said the orthogonal decomposition of this matrix A, real symmetric matrix A, is basically given by A is equal to, let's say, we take that as P D P transpose, right? Where P is the matrix with orthogonal eigenvectors. I'll put this as matrix with orthonormal eigenvectors. This is what we had, right? And we also looked at the action of action of the matrix A on X. We said that suppose we wanted to look at this, and we took a simple example of, let's say, A 2 by 2 real symmetric matrix with distinct eigenvalues, let's say lambda 1 and lambda 2. And let's say we had this the vector U, and let's say you had this vector U and this vector V to be the eigenvectors corresponding to lambda 1 and lambda 2 respectively. And we know that U dot U was 1. We basically normalized it so that the length is 1, and we said that U dot V is 0 because of this property, and V dot V is also, let's say, was a unit vector. So this is what we had. We have already had all these things, and we interpreted the action of AX, the matrix A on X, A being a real symmetric matrix, as we said that we captured this as, let's say, lambda 1 U transpose plus lambda 2 U V transpose X. And what we said was the action of A on the vector X is basically to project the vector X onto two orthogonal axes and scale them, right? What is interesting here, if you see, you just take any two vectors, let's say U and V, orthogonal vectors here, orthogonal, or let's say orthonormal vectors here. We know that the outer product U transpose, in this case U is going to be, let's say, the vector U is going to be, let's say, U1 U2 two component vector, and the vector V is another two component vector V1 V2. Let's take this, right? So we had UU transpose, which was giving me a 2 by 2 matrix. this gave me a 2 by 2 matrix. And what is interesting is this matrix has a rank 1. And V transpose is yet another 2 by 2 matrix. And that has a rank 1. So let's write this. So AX, or the matrix A, is then written as A is equal to lambda 1 U transpose plus lambda 2 V transpose. This is what we had. So if you see, this is going to be lambda 1 times a 2 by 2 matrix of rank 1 and plus lambda 2 times another 2 by 2 matrix of rank 1. And what was this equal to? This was equal to the matrix A, which was another 2 by 2 matrix, but it's of rank 2. Right? It's of rank 2 is what we're going to have. Now, what we're going to say is, therefore, this that we have here, lambda 1 U transpose lambda 2 plus lambda 2 VB transpose, if you see, this is equal to looking at linear combination of two matrices. This is a matrix, this is a matrix. This is a matrix of rank 1 and this is a matrix of rank 1, and lambda 1 is the scalar. And we know that U and V are orthonormal already, which means they are linearly independent. And what's interesting is UU transpose and VV transpose are completely unrelated. That means they are like basis vectors for 2 by 2 matrix. Now what we're going to see is, we see that you can generate a 2 by 2 matrix using this lambda 1 UU transpose plus lambda 2 VV transpose. So basically A is written as a linear combination of two linearly independent matrices. That means, you remember when we did vector space of matrices, we said that this vector space of the set of all 2 by 2 matrices will actually form a vector space of matrices. We looked at that, and then we looked at set of all real symmetric matrices, or 2 by 2 real symmetric matrices. We said that, okay, that's also going to form a vector space, so vector subspace, we said, so of matrices. So what we have here is, this is a way of generating square matrices where U and V are of the same dimension. U is a 2 component vector, V is a 2 component vector, and lambda 1 is a scalar. Based on different scalars, you change the value of scalar, the matrix A changes. That's exactly what we had when we looked at simple linear combination of vectors, where we said, let's say alpha 1 U1 plus alpha 2 U2 plus alpha k UK, some k vectors, alpha 1 alpha 2 being scalars and U1 U2 UK being linearly independent vectors. You keep changing the value of scalars, you end up getting different vectors on the left hand side. That means the linear combination changes, you're going to get different vectors, right? So it's going to, therefore we said this U1 U2 UK, if they are linearly independent, then we said that the linear combination, set of all possible linear combination, is going to be a span of this, and that span is the smallest subspace which contains all these vectors. That's exactly what we are probably even looking at here. So what we are going to do is, if you want to generate a set of square matrices, a real symmetric matrix that you have here, this is one way of doing it. It says lambda 1 UU transpose plus lambda 2 VB transpose. So this is a linear combination. So let's write this. So this is basically linear combination of two 2 by 2 matrices, and UU transpose is actually a symmetric matrix. If you see U1 U2, this is the vector U, and this is U1 U2. So you're going to have U1 square, U1 U2, you haven't got to have U1 U2, and you're going to have U2 square. So this is the matrix. It's a symmetric matrix. It's a real matrix, a real symmetric matrix. So we are going to write this as a linear combination of two 2 by 2 real symmetric matrix, but only thing is of rank 1. So what we essentially say is, look, if you want to if I extend this to say any n by n real symmetric matrix, let's say with distinct, you want to generate n by n real symmetric matrix of rank n, you can actually generate it as a linear combination of n rank 1 matrices, changing these scalars. Now, so the question is, well, this is fine. Does that mean that we can generate only real symmetric matrices? That means you can generate square matrices. Can you not generate rectangular matrices at all? Can we not have something like this to generate rectangular matrices? And that's precisely where we get into the idea of singular value decomposition, which you did, where we had given A m by n, we said that look, this can be written as U sigma V transpose. This exactly has the same representation like what we had there, which was P D P transpose. This also has something like this. So what we did is here we said that okay, I have A is an m by n matrix, so we are going to have this U matrix, which is going to be an m by m matrix, and we're going to have the sigma matrix, which is going to be m by n matrix, and you have this V matrix, which is going to be a V transpose, which V is a square matrix, so we're going to have n by n matrix. So we're going to say this is V transpose, right? This is what we're going to have. Now, if you look at this, we actually arrange this U vectors are all the eigenvectors corresponding to the non-zero eigenvalues of A transpose A. I mean, you have your A transpose, and then V is basically the set of eigenvectors, orthonormal eigenvectors corresponding to the non-zero eigenvalues of A transpose A, and so on. And this contains the square root of our eigenvalues of A transpose A arranged in the decreasing order. So the first one is basically my dominant eigenvalue, the second one is second dominant, and so on. We're going to get sigma r. Suppose if the matrix A is of rank r, which is less than n, we're going to have something like this. Now let's call the first eigenvector to be u1, which has got m components. Let's say this is u2, this has got m components. You say u3, that has got m components. So this is basically an m by m matrix. This is m by n, and that is n by n. And here we're going to have v1 transpose, v2 transpose, etc. We're going to have this, right? Now this exactly looks like what we had there. When we did this PDP transpose, we said there's a recall. When we did this here, PDP transpose was basically this. We had U V, and then we said lambda 1, lambda 2, and we had U transpose and V transpose. This is what we had. PDP transpose. Like this is basically my A. So we said lambda 1 U transpose, lambda 1 V transpose. Then we said lambda 1 UU transpose plus lambda 2 VV transpose. That's exactly what we had. Similar to that, we're going to have something like this. So this is also going to generate my matrix A m by n, which is going to be like this: sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus etc. plus sigma r UR VR transpose. R non-zero eigenvalues we had, and that is going to be this. Now, what does U1 V1 transpose give us, and what does U2 V2 transpose give us, and what does UR VR transpose give us? So let us say the U1 is basically, let's say, a 3 by 3 a three-dimensional vector, say U11, U12, and U13. It's a 3-component vector, and let's say V1 is basically a 2-component vector. Let's say V11, V12. Let's take it this way. Now, what does U1 V1 transpose give? That's basically U11, U12, U13 into V11, V12. So what are we going to get? We're going to get U11, V11, U11, V12, U12, V11, U12, V12, U13, V11, U13, V12. So what are we getting it? Say A is basically a 3 by 2 matrix in this case. Suppose if A were a 3 by 2 matrix, let's say here, let's say A is a 3 by 2 matrix. This is just an example that I'm taking. U will all be U vectors will be 3-component vectors, and V vectors will be 2-component vectors, and so on. So what we get is basically a 3 by 2 matrix. And these singular values that you see, this also correspond to like the scalars that we have. Right? This also corresponds to the scalars that we had in the previous case. So what is this? If you look at the rank of this matrix, this is also a rank 1 matrix. And this guy is a rank 1 matrix. This guy is another rank 1 matrix, etc. And this guy is another rank 1 matrix. So what are we going to do? If A is a matrix of rank R, I'm going to get the matrix A to be represented by as a linear combination of R rank 1 matrices. So SVD in the sum form, SVD has basically two forms. We have the sum form, which is given by summation sigma I ui vi transpose. I is equal to, let's say, 1 to R, and SVD in the product form is basically given by u sigma v transpose. A is equal to A m by n. Here A m by n is basically given by u sigma v transpose. Right? So what we see here, we see that this is also linear combination of R rank 1 m by n matrix, n by n matrices. Right? These are R m by 1, R rank 1 m by n matrices that we have. Now what can we say about U1 V1 transpose, U2 V2 transpose, etc., UR VR transpose? These are matrices of dimension, say, of size m by n each. This is m by n, this is m by n, this is m by n, and each of them are rank 1. And you see that each of these matrices, this basically all these matrices are linearly independent. Why they are linearly independent? Because you see that U1 and U2 are orthogonal to each other, V1 and V2 are orthogonal to each other, and so on. Therefore, the matrix that you get, which is U1 V1 transpose, U2 V2 transpose, UR VR transpose, all these guys are going to be linearly independent matrices. The moment we say linearly independent matrices, we can take these matrices to be the basis for the rectangular matrices of dimension m by n. And what we do is, if you keep changing for different values of sigma I, the singular values, the matrix A is going to change. Right? And that is basically another way to look at your. So SVD in the sum form is going to be used for generating m by n matrices as a linear combination of, let's say, R. R is basically the rank of the matrix, whichever, what is the, you look at the matrix, you want to look at rank R matrices, then you're going to use this. So R, let's say, rank 1 matrices, or let's say, okay, let me just put this linear combination of rank 1 matrices. Right? In case of real symmetric matrix, we used the same technique. We ended up getting real symmetric matrix. We generated real symmetric matrices using rank 1 matrices, linear combination of rank 1 matrices. And here we are going to use a linear combination of m by n matrices, rank 1 m by n matrices, to generate a matrix which is of dimension m by n. So this is your SVD. And what is interesting is, eigendecomposition may or may not exist. Even if you're going to take a square matrix, you may have insufficient number of eigenvectors, therefore the eigendecomposition may not even exist. But SVD exists for all kind of matrices. You can look at singular value decomposition for a single column matrix, a single row matrix, a rectangular matrix which is tall, a rectangular matrix which is wide, a square matrix. You can look for any matrix, let's say any non-zero matrix. You get this singular value decomposition. So it seems like as Professor Gilbert Strang says, and Professor Bitterov also says, like singular value decomposition seems to be the core of the entire linear algebra. In fact, Professor Gilbert Strang even goes to the extent of saying it is from here that the journey into linear algebra begins, right? And now let's just check one more and then try to try to interpret this action of A. Suppose I have this matrix A, which is m by n, real matrix. Right, m by n real matrix, and which has the singular value decomposition, which is given by I is equal to 1 to r sigma I ui vi transpose. Right, I want to look at sigma ui vi transpose. It's very interesting to note that we had this notion of pseudo inverse. We had the idea of pseudo inverse when we studied least squares. We said that matrix A pseudo inverse, this is nothing but like a pseudo inverse of A, pseudo inverse of A was given by A transpose A, the whole inverse A transpose. This was what the pseudo inverse was for a matrix A m by n and of rank n. Right. Now I want to study again the action of AX, like how we did in case of real symmetric matrix. I want to study the action of AX here. What does that mean? In fact, we will actually know what is the what is it to say the let's say the action of A pseudo inverse. What is the action of A pseudo inverse of a matrix? So because we had X dagger, which is the optimal solution, which was given by A transpose A, the whole inverse A transpose B, when B was not in the column space of A. Right? So now we want to find out what does the pseudo inverse actually do to B. Right? We want to figure out what does the pseudo inverse actually does to B, and in fact we want to also look at the idea of what is the effect of this matrix A on a particular vector X. Let's look at that. So how do we interpret the action of A? Interpret the action of A m by n on an n component vector X. Yeah, like how we had this in the eigendecomposition case, we had this to be the projection and scaling, projections onto orthogonal axis and so on. This is exactly what happens even here when you look at the pseudo inverse and stuff. In fact, that forms to be is basically what we have as the cover page of Professor Gilbert Strang's what you call linear algebra textbook, where we have, let's say, the row space of A, the null space of A, then we have the column space of A, and we have the null space of A transpose. So this is null space of A transpose, and this is going to be the column space of A, and this is going to be null space of A, and this is going to be the column space of A transpose. And typically what we do is we say that, okay, here is a vector X, and the matrix A is going to take this vector X and then going to put it in the column space of here, column space of B. So this is going to be AX. And any vector here is going to be taken and put here. This is going to be any vector in the null space that's going to be put at the origin. This is going to be the origin. Similarly, if I have a vector B on this, now what we do, you have this A transpose, which is going to take this vector and then put it in the column space of A transpose. And essentially what we will see is the pseudo inverse is going to do something similar to this. The pseudo inverse is going to first project this vector onto the column space of A, and then find the corresponding X vector, which is that X dagger, and then project that onto the column space of A. And that's exactly what your pseudo inverse does. So everything that we do, every idea of eigendecomposition, singular value decomposition, or whatever that we do, it always has a geometric interpretation. And this is something, this is the crux of understanding all these things like singular value decomposition and eigendecomposition. So what we did now, we basically looked at eigendecomposition, and we also looked at the singular value decomposition. We saw some kind of a parallel between these two guys, and we also interpreted eigendecomposition for a real symmetric matrix as a way to obtain real symmetric matrices as a linear combination of rank 1 matrices, real symmetric matrices, and m by n matrices, rectangular matrices, can be obtained as a linear combination of rank 1 m by n matrices through singular value decomposition. We said that, okay, these are the ways to generate real symmetric matrices as well as matrix of dimension, rectangular matrix of of size m by n. So on that note, I think we've made a compact we understood everything in a compact manner, and then we get into the applications part in the next lecture. Namaste. Thank you.